A very good evening, participants. Today we have Dr. B. Madhan. He's a senior principal scientist from CSAR Central Leather Research Institute, and he's going to talk about collagen stabilization concepts from tanning to biomedical application. I think most of us will be knowing Dr. Madhan, but the journey of Madhan is what I would like to introduce to most of you. Very interesting, and he's been knowing him personally within a department where we are together. Dr. Madhan is a real hard worker, and his work not only in leather, but he has wide expertise in biomedical applications. And the most admirable work, which rather I felt about Dr. Madhan, was the one which he's done for leprosy persons. He healed them, he's approached them, he's healed them, and that was something which most of us should admire his commitment and the knowledge and the science towards curing such people. Okay, anyways, from what Dr. Madhan has sent his bio brief, I would like to tell that uh, he is, apart from being a senior principal scientist, he is also the honorary professor for Anna University, and he holds the MTech leather technology degree. He's also first rank from that degree from Anna University, and he's joined CSR CLRI in May 2002, and obtained his PhD in the Faculty of Technology from Anna University. Post his PhD, he pursued his postdoctoral research through DST, that is Department of Science and Technology, under the Boyce Cast Award Fellowship in the area of biomedical engineering at Robert Wood Johnson Medical School, New Jersey, USA, during the year 2007 and 8. And I think this has brought a change in Madhan, and he started looking at biomedical applications for the collagen stabilization work which he has made. And Dr. Madhan has made path-breaking contributions towards gaining insights in stability and stabilization process of collagen, which have found applications in clinical management of chronic wounds, management of arthritis, and development of sustainable tanning technologies. And Dr. Madhan has transferred a game-changing technology on collagen-based biomaterials for the treatment of chronic wounds, which is available in the market with the brand name C-Skin. He has also been associated with rehabilitation of leprosy cured but deformed persons at Sri Ramakrishna Mutt, Chennai. This is what which I personally admired Dr. Madhan for. And Dr. Madhan has conceptualized the project on research initiatives for waterless tanning. He was part of the team, and as this was as part of the 12th five-year plan projects of the government of India, which CSR CLRA executed. And this, of course, this did lead to path-breaking technological uh, innovations. And Dr. Madhan has more than around 120 publications in highly reputed international journals and 15 patents to his credit. He has participated in several national and international conferences and symposias, and several papers published by Dr. Madhan has received wide citations. Recognizing his contributions to the understanding of tanning and potential impact of his research in biomedical applications, he was awarded the CSAR Young Scientist Award in 2009. He also received the Young Engineer Award and Indian National Academy of Engineers Award and Institution of Engineers Award in 2011. And in 2017, Dr. Madhan, as part of the CSR CLRA team, received the FICCI R&D Award, CSR Technology Innovation Award, and NRDC Meritorious Award for the development and translation of waterless chrome tanning technology. And Dr. Madhan has been associated in several international capacity building projects. And this is what I tell. I generally talk about Dr. Madhan being hardworking. He's always on the move, and I sometimes generally ask Dr. Madhan, when do you sleep and when do you get up? So early morning, 5 o'clock. If I have something to say, he's online and he replies immediately. I mean, when we work on certain projects, where when I ask him, he's available even in the morning, and he sleeps very late as well. So that is why I indicated he's a very hardworking individual, and his wide expertise not only in leather but in biomedical engineering. Uh, he's associated with many projects related to capacity building at Vietnam, Ethiopia, Kenya, Rwanda, etc. And Dr. Madan believes and strives in progress of nation by creating value for people through science, engineering, and technology. So, on behalf of ISLW webinar series, may I now request Dr. Madan to kindly give his presentation, please.
Yeah, thank you, Dr. Swarna, for the nice introduction, and good evening to everyone. I hope all of you are able to see the screen. Right? So, are you able to see the screen?
Yeah, screen is very much visible. No problem.
Yeah, thank you. So, though I have the passion in pursuing, research on development of sustainable technologies to provide solutions in leather manufacture, so today's, presentation I chose, to focus my pursuit with the leather making protein, which is collagen, with an objective to leave behind a different perspective and to leave some thoughts to ponder, after my lecture. So that's why I have chosen this topic for today. So I started my research way back in 1999. So, one of my initial works were on the development of chrome-free tanning. I was trying different options for tanning, like I was looking at aluminum-based, silica, zirconium, vegetable acrylic, vegetable aldehyde, as a part of my efforts to find an option that would be as versatile as chrome tanning. So during these pursuits, I had come across questions, though tanning being age-old process, whether do we understand the stabilization of collagen at molecular level? So when I tried to address some fundamental questions on collagen stabilization, I was not still satisfied. So I started asking much more deeper questions, like, did I understand the factors that would contribute towards the stability of collagen? So as we go deep, some questions, pertaining to as basic as biosynthesis of collagen remains, unanswered even today. So I moved on, from the fundamental curiosity, addressing, passion-driven research to solution science. So in this lecture, I will share my research journey on collagen that led to solutions for biomedical applications. So let me also try, to use a mouse here. Yeah, okay. Right. Hopefully, I think the mouse is, visible for all of you. Okay, so it is, for making leather. So we use hide and skin, and the matrix. Finally, when we convert into leather, it is nothing but collagen. Therefore, we call collagen the leather making protein. And it is one of the protein which had lasted, with highly conserved protein in the evolution space, which means the protein samples that had been sourced from the dinosaurs, particularly the bones, and the collagen that we have today, genetically it has a highly conserved. They are very, very similar, 99.9% similar. So which means this is one protein which had lasted time tested in the evolution space. And till date, 29 types of collagen have been identified. And all these collagen, the common thing of all these types of collagen is the triple helical structure, so which has 3 polypeptide chain. And out of 29 types of collagen, and type 1 collagen is the most abundant, collagens. 1 type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, collagen. And type 1 collagen is the most abundant, colla which are present in the connective tissues. And for all these types of collagen, the major role, as a part of the mammalian tissues, is to provide the structural integrity and rigidity for the connective tissues. So wherever you want, the body to have perform a structural role, for in the case of skin, the major solid component of skin being collagen. So skin, it needs to perform the function of protection. So if you take bone, it needs to perform the function of bearing the load. So you will find cartilage in all these connective tissues, you will find collagen in them. And the type 1 being the most predominant of all of them, which is found in skin and bone. So the only difference, between skin and bone is like, in the case of bone, it gets mineralized. I'll explain as we move on. So I would always like to acknowledge, whenever I talk about collagen, I would like to acknowledge the great contribution from Professor G.N. Ramachandran. So in fact, immediately after, he finished his PhD from Cambridge in 1953. So when he came back to Madras, he was offered a position at the University of Madras, the physics, he was heading the physics department. And at that point of time, the double helical structure was deciphered by Watson and Crick, in 1953. So immediately within a year, he came out with, during those period, a lot of people were trying to solve the structure of collagen. And GNR was the first person to solve the triple helical structure of collagen. And in fact, this was even at that point of time referred as, Madras triple helical structure. So that was a great contribution from GNR. And he also went on to, provide us a biophysical basis for how a protein can take, form different structure in three-dimensional space. So with reference to the supramolecular assemblies of type 1 collagen, so what you see in the bottom of the screen, starting from a polypeptide chain. So, I was mentioning in the case of collagen, for all the types of collagen, it is a triple helical structure. So it has 3 polypeptide chains. So the frequent, the primary structural repeat of each of the chains is the GXY, where glycine is the simplest and smallest of amino acids that, you can find in nature. And then X and Y are occupied by other amino acids. But X and Y are frequently occupied by amino acids such as proline and hydroxyproline. And hydroxyproline is an amino acid which you will find only in collagen. And in fact, hydroxyproline is a post-translational modification. During the biosynthesis of collagen, from the, usually in biosynthesis of collagen, there are specific genes which would correspond for the synthesis of collagen. In the case of type 1 collagen, there are 2 genes, which is called as COL1A1 and COL1A2. From the genes, there is RNA which will read the codes from the gene, and then it gets translated a sequence of amino acid. And then after this 3 polypeptide chain production had taken place in the ribosome, this hydroxyproline happens as a part of post-translational event. There are many post-translation events that occurs as a part of collagen biosynthesis. So then but what is very critical is this repeat of presence of glycine at every 3rd position. I will in the subsequent slide will try to show you how critical and important that glycine amino acid to be part of every 3rd amino acid in collagen. So from this polypeptide chain, it builds into a triple helical structure. From the triple helical structure, the triple helical molecule, as they come out of the cell, cells are the ones which will produce proteins. From the, in the case of collagen, it is the fibroblast cells. In the case of skin, in the case of, if you take bones, it is the osteoblast cells which will produce collagen. So as the collagen molecule come out of the cell, there are again post-translation events which will clip off. There are some enzymes which will clip off the end-terminal domains. As soon as that clipping happens, immediately the collagen would aggregate, would self-associate to form supramolecular assemblies to form fibrils. It's a highly ordered arrangement. So this is referred as a quartered staggered arrangement, because one molecule of collagen in linear space, it assembles periodically, after about 670 angstrom. In the lateral space, it gets overlapped 1/4 of the distance from the previous molecule, and hence, this is referred as a quartered staggered arrangement. And this is a highly beautifully organized arrangement. So what you see on the top here is a fibril, which is actually observed in a electron microscope. So this is created because of the gaps and overlap regions. In these gap regions that you see here, in the case of bone, it gets mineralized with calcium phosphates. And that's why bone is more brittle, whereas skin is not so brittle. In the case of skin, there is no mineralization happens. Like that's why, as we move from, the molecular level to the tissue level, as the supramolecular assembly, hierarchical ordering of collagen. So we have very little knowledge as we move in the structural space as it goes into a tissue. Whereas at the molecular level, particularly with reference to the structure of collagen, today we have an in-depth understanding about what contributes towards the structure of formation of polypeptide chain and then a triple helix, and how it gets assembled to form fibril, and how. But then from fibril to fiber, what controls the diameter of fiber in the case of skin, and particularly in skin tissues, and how it is different. So what are the cellular events, physiological events that controls to differentiate different layers in skin is also, it's a bleak area. Similarly, so what is those factors that actually control the fiber diameter? So like for example, if you take a bone, the fiber diameter can go 100 nanometer. Whereas in the case of skin, it goes up to like 300 nanometer. In the case of cornea also we have the same type 1 collagen. In the case of cornea, you cannot go like beyond anything above 60 nanometer, because so cornea, it's very important. It remains completely transparent for the light to pass through the eyes. So therefore, in the case of cornea, it gets restricted to about 60 nanometer. So otherwise, if it builds beyond 60 nanometer, like what happens in the case of skin, it's about 300 nanometer, it becomes opaque. So that's why, there are beautiful organization that the nature does this differentiation. Those processes still we do not, understand thoroughly. Even as I was mentioning, like, during the biosynthesis of process of collagen. So collagen, each molecule, it's about 300 nanometer. Like particularly tropocollagen, if you take it, is beyond 300 nanometer. Like, recently, I was at the Gordon Research Conference of Collagen in 2019, where people are trying to, perplexed that there is a cytoplasm, from the rough endoplasmic reticulum, when the collagen is transported out of the cell, it is carried by vesicles, and these vesicles are in the diameter of only 100 nanometer. So with a diameter of 100 nanometer, how is it possible for a collagen molecule which is of the size of 300 nanometer is being folded? It is found out, so that it kind of bends, and to get accommodated within that, and that is how. So I was kind of perplexed. Even today, so we do not know, there are so many events that happens which as a part of biosynthesis of collagen. So I would like to present a few of my work which would clearly indicate the importance of glycine contributing towards the triple helical structure. And I was mentioning glycine XY repeat, particularly in the case of type 1 collagen. If you see, this glycine XY repeats 338 times, which means there are about 1,000, let's assume it for like 999 amino acids which are in the triple helical domain, or 1,000 amino acids which are in the triple helical domain. They will have a sequence of GXY, GXY, GXY. Out of the 338 glycine that are part of each chain, even if one glycine, if it is mutated to any other amino acid, it results in a genetic disorder called as osteogenesis imperfecta, which is in simple terms are called as brittle bone disorder, right? So now this osteogenesis imperfecta would present a very varied phenotype. So it can present perinatal lethal, like which means the child can be born dead even in the mother's womb, to some mild phenotypes. And that again depends on the what amino acids would mutate glycine, right? So this is one of the very critical. So this clearly indicates to us even one glycine missense mutation, it has a very significant impact on the overall structural formation of the human anatomy. And why is this so critical? Is triple helix cannot be formed at all. Again, it depends on what amino acid. Like I was saying 3 chains. Like in the case of type 1 collagen, there are 2 genes. So 2 chains would have the same primary sequence, which is alpha 1 chain, and 1 chain which is referred as alpha 2 chain is slightly different. So depending on which chain the glycine mutation happens, the severity would be varied. If there is a mutation in alpha 1 chain, so there are going to be 2 mutations. 2 chains are going to be mutated. Therefore, the severity will be much more higher compared to a mutation that happens in a alpha 2 chain. And again, from where usually collagen. So we start I was mentioning the number of amino acids is somewhere about 1040 amino acids. So we have the numbering starting from N terminal to C terminal. Of course, in between we have peptide bonds, NH-CO. So NH2 and it ends with COOH. And once these 3 chains are assembled as a part of biosynthesis process of collagen, usually folding will start from the C terminal. After all this post-translation modification happens, it starts folding from the C terminal and it zips through all the 3 chains. There are hydrogen bonded interaction happens between one chain and another chain. And between these 3 chains, there is hydrogen bonded interaction which holds the 3 chain together to form a triple helical structure. So therefore, if there is any mutation closer to the C terminal end, irrespective of whatever is amino acid, they all happen to be a lethal mutation, which means it leads to lethality. So like, the child, including perinatal lethality, the child cannot be, life of, child will be questionable, even it will not be formed properly. Similarly, any mutation that happens in the N terminal end, they are not going to be lethal. Right? Again, because the momentum, once it starts folding, the momentum takes care. So therefore, any mutation closer to the N terminal, mostly they are not lethal. But whatever that happens in between, it depends on what amino acid that mutates for glycine. So just to illustrate the significance of this glycine, so we have used peptide models. This is a peptide models. In the case of, it's a collagen-like peptides. We are trying to mimic a collagen polypeptide chain using a peptide model where, so we have a peptide synthesis having GXY sequence. Glycine, P refers to proline and O refers to hydroxyproline and A is alanine. So, what is being done here, you can see, now we develop peptides, just changing, there is about 33 amino acids in this peptide. We have replaced one glycine with alanine, serine, arginine, and aspartic acid, 4 different peptides. And you can clearly see, we can also look at the melting temperature. So thermal stability of the triple helix, by using circular dichroism experiment. And what you see in the black, okay, it corresponds to the control peptide, where it normally folds into triple helix having a melting temperature of 35 degrees centigrade. And you can clearly see that glycine, when it is replaced by alanine, the melting temperature drops drastically to 15.5 degrees centigrade. But then still it folds into triple helix. So, how do I know it folds into triple helix? I could see a baseline. So both in the case of alanine and serine, still I could see a triple helical folding. Whereas in the case of glycine, replaced by arginine, it does not fold into triple helix at all. In the case of aspartate, it does not fold into triple helix. Because in addition to the size these are bulky side chains. So there is a huge amount of spherical distortion which will not allow the triple helix to come together at all. It causes so much of bulge. So, it puts three chains apart. So therefore, the hydrogen bonded can not exist anymore. So that's the case of arginine and aspartic. So more than the size, we also need to take into account of the charge. In the case of aspartic acid, it has a charge repulsion. In the case of arginine also, there is a charge repulsion. In all these peptide cases, we use normally it's a homotrimer. Usually, when we synthesize the peptide and take them in solution, they have a thermodynamically favorable situation to immediately fold into triple helix. So that's what we normally do: prepare a peptide and put them in solution, heat them, and then we allow them to refold. It forms a triple helix immediately. And that's how it's so significant that glycine protein is so significant that it contributes towards the stability of collagen triple helix. You can see here what happens. So all the three chains are being listed. Particularly if you see here, each of these chains would have a left-handed helical twist, and all the three chains together has a right-handed superhelical twist. So you see here, whenever each of the chain, so you assume this as a central axis, whenever each chain comes towards the central axis, all of them happen to be a glycine. So again, when the polypeptide chain folds comes towards the central axis, it happens to be glycine. So when this glycine, if they are occupied by, glycine is the smallest amino acid. The side chain will have only 2 hydrogen. The next smallest amino acid is alanine, which will have 1 carbon and 2 hydrogen more. So it cannot even accommodate 1 carbon atom, or even 1 carbon atom is going to create a spherical bulge. Because of the spherical bulge, the distances between the chain will increase, and therefore each chain will not have an influence on each other because the hydrogen bonding cannot form. So one of the very important factor what holds these 3 chains together is the hydrogen bonded interaction that happens between the peptide bonds of one chain and another chain. Okay, if you have chain A, B, and C, there is an hydrogen bonded interaction between chain A to B, B to C, and C to A. And that's what keeps these 3 chains together. Therefore, larger residues are harder to be incorporated for glycine, and hence it happens to be a lethal mutation inhibiting the folding of collagen to form a triple helix. Coming to collagen stabilization, some of the fundamental question that I wanted to address to gain molecular insights on vegetable tanning is that should a tanning agent, should it cause such structural alteration to collagen that makes collagen or the whole skin non-degradable by the enzymes? Otherwise, usually collagenase is the enzyme which is capable of breaking down the skin. Like if you take the skin and if you just don't tan it and then throw it out, natural decay is going to happen. In the process of natural decay, so there is a autolytic, enzymatic degradation sets, and apart from that, there is also bacterial, colony which will form, and particularly, there are certain anaerobic bacterial colony, particularly species such as Clostridium histolyticum. They will start producing bacterial collagenase, and these collagenase are the only enzymes which are capable of breaking down collagen, therefore skin getting degraded. Now, the question that I wanted to address was whether whether these tanning agent, should it change the inhibit the protease, or should it create such a structural alteration in the collagen so that the protease does not recognize? So to address some of these fundamental questions, I used polyphenols, which are precursors of condensed tannins such as catechin, quercetin, epigallocatechin gallate. And for hydrolyzable tannins, I chosen gallic acid, ellagic acid, tannic acid. So I looked at the shrinkage temperature changes using the molecular species. What happens generally in vegetable tanning process? So when we use wattle extract or myrobalan extract, it is a mixture of several species. So it will have a mixture of, because it has a very molecular weights. It has more than 10 or 12 different species at varied sizes. So therefore that influence will be different. That is why it is important to gain such molecular understanding to go with small molecular smaller molecules such as quercetin, catechin, or epigallocatechin gallate, and looking at their thermal stability using the fibers, collagen fibers. So similarly, the thermal stability when we use the precursors of hydrolyzable tannin. So you can see even the molecular species such as tannic acid, which is a nonyl galloyl glucose. It has a, the hydrolyzable tannin has a glucose core. To the glucose core, it is attached through a glycosidic linkage. You have a gallyl units. So there are about 9 gallyl units. So when you have 9 gallyl units, each gallic acid would have gallic acid is nothing but a trihydroxyphenoic acid. So it has 3 hydroxyl groups. When we talk about nonyl galloyl glucose, so we are talking about 3 into 9, 27 hydroxyl groups being present. So predominantly all these vegetable tannin molecules have hydroxyl groups, the phenolic hydroxyl groups, and therefore it is anticipated these hydroxyl groups would interact with collagen, exhibiting hydrogen bonded interaction mostly. So to address the question whether these polyphenols, can they bring about any structural changes on the collagenase? So we've looked at all these polyphenols, including catechin and epigallocatechin gallate, are able to bring about a complete transformation into the structure of collagenase. So which means these polyphenols can inhibit, standalone, the polyphenols can inhibit collagenase. So therefore, once a small molecule inhibits an enzyme, enzyme and substrate reaction are highly specific. So if a catalytic domain is inhibited, those enzymes will not be exhibiting its activity. It may lose its activity. Similarly, if polyphenol inhibits collagenase, particularly here we used bacterial collagenase to study, because bacterial collagenase is highly, much more degradative compared to mammalian collagenase. So bacterial collagenase can cleave off collagen than 6 different sites. So whereas quercetin did not bring about a very significant change in the structure of collagenase. So similarly, we also found, tannic acid and myrobalan having a similar effect in bringing about a degradation on the collagenase structure. So we also looked at the ternary system as how a rat tail fiber, when it is treated with polyphenol and then that is subjected to collagenase treatment, when these are smaller molecular species, when we use like gallic, ellagic, quercetin, and catechin, the degradation is not so significantly greater compared to native collagen. If you see, at a time point of somewhere around 96 hours, a native rat tail collagen fiber gets degraded more than 95% for a normal control. Again, we use collagenase as a ternary system. So whereas as we use other small molecules, the degradation of collagen decreases. It decreases to a point where catechin presents itself only about 35% degradation as against 90% degradation of a native fiber. Whereas if you see epigallocatechin gallate, if you look at the x-axis, the degradation is very, very low compared to what we have seen in the case of catechin or the gallic acid. The degradation here is less than 4%. Now, I was also trying to understand at molecular level what happens, using theoretical molecular modeling techniques to see what are the sites at which these polyphenols would interact with the triple helical structure of collagen. So we looked at different functional groups present in collagen which would bind with these polyphenols. And interestingly, so what we found out, protein is expected to exist in some preferred conformational arrangement. So similarly, collagen triple helix also would exist in a preferred conformational arrangement. It's because of those inter chain interactions between the 3 chains, and therefore there are some sites which are exposed to the solvent or solute, and that will vary depending on the conformational arrangement. Now, small molecule and the solvent can compete for the vicinity of the protein. So here in this slide, what we could clearly see, we were looking at solvent accessible volumes or solvent inaccessible volumes, and it clearly correlates linearly with the binding energies. with the binding energies, of various complexes that we looked at collagen. So now, having understood the processes associated with vegetable tanning, can I use this concept to manage autoimmune disorders such as arthritis? Right. So actually, again, so I wanted to relate some of these, mechanism associated with vegetable tanning to applications such as, such biomedical application, including arthritis. So, some of my papers, all those molecular level understanding as a part of vegetable tanning was my research work done as a part of my PhD in early 2004, 2005, and papers, a lot of papers have been published. So there I would relate a concept associated with solvent inaccessibility, as a consequences in managing, arthritis. So arthritis again is an autoimmune disorder where there is an onset, which a normal tissue is considered to be a foreign, and then there is an onset of a lot of immune responses, which will start breaking down our normal tissues. So when I presented this concept, there are rheumatologists, in New Jersey. He really liked this concept. So, and he also believed the possibility that these polyphenols interaction with collagen could inhibit, collagenase accessibility to the tissues that are part of associated with articular cartilage. So coming back to what happens in the case of arthritis is, so now, like, it is when we have two knee joints, you will have a bone. Between the bone, there are joints. And the joint tissue provides a cushioning effect. It is primarily made out of type 2 collagen. So the interesting fact about type 2 collagen is it's a homotrimer. And also another interesting fact about type 2 collagen is the turnover rate, particularly in the cartilage tissue. The turnover rate of type 2 collagen is about 117 years. So in the case of skin collagen, type 1 collagen, the turnover rate is somewhere about 6 to 8 years. In the case of tendon type 1 collagen, the turnover rate is somewhere about 20 to 30 years, 20 to 22 years. So which clearly indicates any damage that happens to the type 2 collagen, it kind of remains a permanent damage. That's why there's arthritis, it is what happens, the cushioning tissue that I was referring, which is between the two bones, which acts as a shock absorber between the bones. And there is a fluid between these two cushioning, shock absorbers. And it has a very low fluid there. So somewhere, during aging, there is a onset of biological mechanism which gets triggered. There is no, even today, people have not understood what are all the mechanism by which this arthritis gets triggered. But what people have understood is the damage happening to the cartilage remains permanent. So you cannot avoid. Okay, so if you look at the structural composition of this articular cartilage, it has predominantly type 2 collagen, and it also has proteoglycan, particularly aggregans. These aggregans are reversible, whereas any damage that happens to the collagen, it results in an irreversible damage. Therefore, so these are the organization associated with the articular cartilage. So therefore, I tried to propose the concept of, can I do vegetable tanning of cartilage so that I prevent the degradation of cartilage permanently? Okay, that was the concept. Usually what happens in the case of cartilage, in the case of type 2 collagen also, it's a fibril forming collagen. So these fibrillar tissues are the final event of arthritis is the breakdown of this fibrillar collagen by collagenase. So this collagenase will break down specifically. So once the breakdown of collagen fibril happens, the recovery is very, very low. As I was saying, the chondrocyte cells has a very poor ability, particularly in cartilage, to synthesize type 2 collagen. And therefore, whatever damage that happens to the collagen fibrils in chondrocyte, that remains a kind of permanent damage. So therefore, in the case of patients, where we can sense the onset of rheumatoid arthritis, like rheumatic factor from the blood, one can detect this RF factor. So once, if we are able to detect a patient, at the early stage, we can do a tanning by using this plant polyphenols, where we can inject, through a microsphere, and where these polyphenols can come out in a controlled manner and interact with these fibrillar collagen, and thereby this articular cartilage collagen can gain resistance against collagenase degradation. So to test this hypothesis, and now once after interaction of these small molecular weight polyphenols, collagenase cannot break down collagen fibrils anymore. To test this hypothesis, we have taken a bovine articular cartilage, so harvested from a bovine. So we have taken only the articular cartilage, which will primarily have type 1, type 2 collagen, and then looked at its degradation profile after treatment with these small molecular weight polyphenols. And we found out particularly the epigallocatechin gallate and tannic acid exhibited a significant resistance against degradation. Both the degradation of glycosaminoglycan were also prevented, and as well as the type 2 collagen degradation was prevented. To prove this hypothesis using a rat model, so we have developed, there are rat models that are available to induce arthritis. Okay, usually, so when we use mycobacterium, not the tuberculosis bacterium, along with type 2 collagen. So if we can inject into the rat, particularly once we inject to the tail, it creates an arthritic model. It's a very well established model. So now what you see on the top left, okay, top left, which is a normal control, which is a rat which is not induced for arthritis. Whereas what you see as PPC is a negative control, where the rat were induced for arthritis, but they are not being subjected to any polyphenol treatment. And what you see as PT is a rat which have been treated with tannic acid, and E is epigallocatechin gallate. So now this is a group of rats which were prophylactically treated, which means prior to the induction of arthritis in the rat, we injected intraarticularly these polyphenols in a controlled manner. So after injecting the polyphenol, then we induced the arthritis in the mice, and we found out a significant reduction in the degradation score for both the case of tannic treated and epigallocatechin gallate treated rats in the intraarticular space. Similarly, we also looked at inducing the arthritis first, and then immediately start the treatment intraarticularly with these polyphenols. Even in that case, we found a significant protection of the articular cartilage. You can clearly see what you have in the case of epigallocatechin gallate and tannic acid. Both of them almost resembles to the normal, rats, the intraarticular space of the normal rats. Whereas the positive control, you can see a complete degradation of the cartilage tissues. So with this, we are able to prove this concept that it is possible to protect the articular cartilage against arthritis. So as a treatment strategy, we also had developed methodologies where we developed the microspheres, which is in the order of about 15-20 microns, and loaded polyphenols into that. And then these polyphenols can come out into particularly between the articular cartilage. So we have a synovial fluid, which is about, it will have a volume of about 1 to 2 ml. So, and this synovial fluid will have a turnover rate of about 6 hours, 6 to 12 hours. So if we inject polyphenol into the synovial space, and these are made out of polycaprolactone, microspheres, which are biologically acceptable, microspheres, which will degrade with a time span of about 2 to 3 months. Within this time span, these polyphenols can release in a controlled manner, and then only bind. We will use polyphenol in such a way that only the surface of the articular cartilage is bound by these polyphenols, thereby it gains stability against the collagen-lytic degradation. Because whatever be the biological onset, the final mechanism which leads to a permanent damage to the cartilage is the degradation of the cartilage by collagenase, which is irreversible. So by this mechanism of interacting polyphenols with the cartilage, I can prevent the degradation. And of course, this has been now accepted by the community, and it has been published in one of the high impact journals. Now, from the arthritis, I also wanted to use the concept of stabilizing collagen and developing materials for management of chronic wounds. So one of the problems with chronic wounds is, particularly, when I mean a chronic wound. So usually, if you see a normal wound, if a normal people like, who doesn't have any other, comorbidities, the phases of wound healing is once you have a damage, and then there is a macrophage which will clear off the damaged tissues, and then the inflammatory phase will set in, then a proliferative phase, and a tissue remodeling. This is a normal phase. Now, what happens in the case of chronic wound situation, particularly for patients who have wound, who also have diabetics? This wound would remain in an inflammatory phase. It will always be in inflammatory phase, where there is usually this wound healing process. There is a balance between degradation of normal tissue versus regeneration of new tissues, new collagen molecules. Okay, so now this balance would always be tilted towards regeneration. Therefore, any wounds which are formed in patients who have diabetics, who have other like venous ulcers, so in the case of lepromatic ulcers, all those wounds would remain in an inflammation phase, where in that inflammatory phase there is a high amount of these collagenases, matrix metalloproteases. Collagenase is a matrix metalloprotease because for its activity it requires metal ions such as zinc. So this collagenase would highly elevated in the wound site. So therefore, what happens always, there is a degradation of collagen tissues keeps happening, and there is a decreased activity of growth factors. And therefore, so if generally it is widely accepted for several decades now that collagen-based biomaterials are one of the very effective advanced wound care materials to promote the healing of chronic wounds. But then, the conventional materials that are available in the market, okay, so if you use a dressing material made out of collagen, and if you use them for a chronic wound, and because of the higher elevated amount of these matrix metalloproteases like collagenases, they are going to break down the collagen, very quickly. So why these collagen materials work effectively is that it acts as a sacrificial host, and it provides a lot of nutrient locally at the wound site for the collagen synthesis to happen, and it also acts as a matrix where these fibroblast cells can become comfortable and grow and start producing new molecules of collagen. So therefore, the tissue remodeling can happen faster. Okay, now the strategy what I had developed here was, now the conventional materials, when we use it in the chronic wound situation, the turnover rate will be very high, which means you may require to change the dressing almost every day, sometimes like twice a day also, depending on the nature of the wound. So, and then imagine one small material of collagen which is available in the market from big multinational companies like Johnson & Johnson, Smith & Nephew, Centrogenics. A small 5 centimeter by 5 centimeter material would cost anywhere between $15 to $20, which is, let's say, in our rupee terms, let us put it in simple, 1,000 rupees per material. And then if you are going to change, and this chronic wounds, it will take a lot of time for it to heal. So many times, we think wound is just a simple thing. In reality, particularly for patients, who have diabetics and other, hypertension, other comorbidities, it becomes really complicated. Many a times, it gets very complicated, and that's when patients normally go to a doctor. And particularly in Indian scenario, we Indian patients cannot afford changing a material which is 1,000 rupees. You require like 2 months of treatment. So imagine for 2 months, just the material cost alone, 60,000 rupees, and imagine the cost associated with doctor. And in USA, a diabetic wound would go anywhere about like something like $10,000 to $20,000, the treatment cost, particularly when you use such advanced wound healing materials. The other option to quickly heal the wound is skin grafting. That requires surgical procedure. So therefore, our approach was to reduce the turnover rate at the wound bed and also make an effective material and also an affordable material. So the knowledge that we had gained while understanding the concept associated with vegetable tanning was gainfully utilized in developing a wide range of materials in my lab, such as collagen chitosan tannic scaffold and collagen peptide chitosan based scaffold, collagen silica and curcumin scaffold. There are various scaffolds that we have developed in the lab. So our objective was to make it highly effective and affordable. So here I'm just showing one such scaffold. It's a collagen sponge, which is loaded with microparticles, silica-based microparticles, and these silica microparticles would contain curcumin. So why do I have to use this curcumin? Is one, I was mentioning, this wound, chronic wound would remain in an inflammatory phase. And curcumin and other plant-based polyphenols are also highly antioxidative in nature. So it reduces the reactive oxygen species in the wound bed so that it pushes, the proliferative phase where the cells can start growing, the fibroblast cells can start growing and starts producing collagen. So to have such kind of biologically active molecules to trigger the growth of normal tissues, we resort to such small molecules. And other advantage of these small molecules is they also bind with collagen, thereby the degradation by collagenase is lesser. So therefore, this material at the wound site would remain much more than the normal materials that are conventionally available. And also we were able to design materials with appropriate porosity. So porosity is another important requirement for the cells to bind within the material and then the cells to grow and proliferate. Compared to normal collagen scaffold, some of the scaffolds that we developed in the lab had an appropriate porosity in the order of about 100 microns, which is very important and critical for a tissue engineering material. And these are some of the experiments what we do in lab to determine in vitro, like what you see is the collagenase degradation, and one of the material clearly indicates lower collagenase degradation compared to a normal collagen scaffold. Like what you see in the case of normal collagen scaffold, it degrades within 12 hours. Whereas the scaffold developed by us, it can stay beyond 72 hours. And at the same time, these scaffolds are very good for the fibroblast cells to get attached to the scaffold and start to grow and in turn produce collagen. And typically we conduct to test it in the in vivo model as a preclinical evaluation. So what you see on the top is a control. So normally we create a full thickness incision wound. 2 centimeter by 2 centimeter wound is created, and we monitor the progress of healing with time. So MNC refers to a multinational company material, and there are 2 materials that I have used as a positive control to compare the material that developed in my lab to test it, how it performs as against these multinational company brands. What you could see clearly is after day 15, in the case of control, it did not heal even after day 15. So in the case of control, typically complete healing happens about 23rd or 24th day. Whereas in the case of multinational company brands, they also did not heal completely even at day 15. Whereas the metal developed in our lab is able to completely heal within about day 15. One, you can also see the metal being intact at the wound bed. So even at around day 5. So which clearly indicates that this dressing material turnover rate is lower as anticipated. Therefore, the dressing changes can be reduced and the effectiveness of healing the wound is also better. And the cost is also definitely much lower. And this is, again, technology has been transferred, and this is available in the market in the brand name as C-Skin. And these materials have been used. Dr. Sarna was pointing out the work that we did at the Sri Ramakrishna Mutt. In fact, Ramakrishna Mutt, they have a mutt. They particularly in Ramakrishna Mutt at Mylapore, they have a rehabilitation program for the patients who have been affected by leprosy, but of course they are cured by leprosy. But then whatever damage this Mycobacterium leprae had created in the patients, particularly whatever the wounds, the nerve damage that remains permanent. So one of the problems with the leprae bacterium is, we do not know. The incubation is very low, and gradually it starts, breaking down the nerve cells. What happens? We lose our senses. So once we lose our senses in the limbs, particularly in the limbs, so we don't have the perception of the pain. Okay, so since we don't have the perception of the pain, any ulceration, any damage, physical damage, it gets complicated. So since there is no appropriate response are there, so the healing also gets affected. So one of the most challenging, wounds to heal is the, patients who are affected by leprosy. Those are the wounds which are most challenging. Though they have been now cured of the bacterium, there are a lot of drugs that have come, which leprosy patient they have been cured of the bacterium. There are a lot of multi-drug strategies that are available today to kill the bacterium. But then whatever damage that the bacteria has done on the patient, it remains kind of permanent damage. And that is why, though they are cured of leprosy, they have to be deformed. That's why these group of people are referred as leprosy cured. They no more would transmit to anybody because they don't have the bacterium. But then the deformation remains, kind of permanent. They have to live with these wounds. Many patients, have to live with these wounds, and then their whole social, life is completely lost. They become a burden, for the family. Not only them, even today, diabetic wounds are becoming much more complicated. So India being a diabetic capital of the world, if you look at the statistically, there are about 70 million people annually are affected by diabetes. So out of 70 million people, so at least 15% of the people are being exposed to wounds in one form or the other. So out of this 15%, which is somewhere about 10 million people, 1 crore people annually affected by wounds, who are having diabetes affected by wounds. Out of them, 15% it results in a mutation, and it results in a like you need to cutting off the limbs. All those things would happen. So you have to, the people are getting resorted, they lose the limbs. So once individual loses their limbs, it becomes a very big social burden. Wound burden for the country is one of the very big social burden in the years. Already it is there, and in the years to come, it is going to get aggravated. It's not going to decrease. Therefore, so what here I would clearly demonstrate here is, from our lab, we used to, every Saturday, they used to have this leprosy camp, treatment camp every Saturday. So every Saturday we used to treat all the leprosy patients, those who are having the wounds. Here I could clearly indicate some of the patients who had 5 years of wounds not being healed. The magnitude of wound is unimaginably huge. And for example, in the patient, where on the top right, so this wound was created because he did not have the feeling of pain. there was a sharp, object that had pierced into the wound. That is how that wound was created, and it was a very deep wound when he came. So it got healed in like about 34 dressings. Similarly, there is a lady who had a wound history of 5 years, it did not heal. So with about 46 dressings, it got healed. So there is another. So there are, as of now, there are more than 50 patients that we had continuously had been there at the MUT for a period of somewhere between 2015 to 2017. We were able to heal about more than 50 patients who have been affected with the chronic wounds. So therefore, so from a passion-driven research, so here we have a solution-driven. So it is very important that from a passion-driven science to come out with solution-driven science. In this case, I had adopted the concepts that I gained, fundamental concept that I gained in understanding the mechanism associated with tanning, and it helped me in design and solve bigger problems, let it be arthritis or chronic wounds of diabetic patients or any chronic wounds. As I was mentioning, a diabetic ulcer is one of the major concern for the Indian population, and materials that have been developed, which is available in the market, are very low cost, compared to what is available in the market, and lesser dressing requirement and faster healing. So since 2017, it had clinically benefited several thousands of patients. So I would like to leave this August gathering, with some thoughts to ponder. So I would like to, here indicate, while we make leather from the hides and skins. So if you look at 1 ton of raw hides and skins, so we have somewhere about 300 kilograms of collagen. And out of that, so what is finally getting converted is only about 140 kilograms of collagen is getting converted into leather. So whereas about 150 to 160 kilograms of collagen, we now lose them, either in the form of trimmings, we lose them in the form of untreated, chemically treated form, or untreated form in the form of chrome shavings, in the form of splits, in the form of finished trimmings. So ultimately, if you see, we lose somewhere more than 50% of collagen during the process of making the leather. So, if you are in a position to tap that collagen to make certain valuable products, we can certainly make the leather industry much more sustainable than what it is today. So with this thought, I would thank all of you for your patient listening. So I'll be happy to take up questions pertaining to leather or tanning or biomedical applications, whatever that I've presented. Thank you.
Yeah, thank you very much, Dr. Madhan. It was really enlightening and could be eye-opening for many of us here to show way forward for applications to a waste that can come out of our industry of high such value. And we are very happy to see you in this endeavor. And probably now we would go with the questions. I would request, if somebody has any questions, could you please raise your hands, because it's easy to monitor. Okay, okay, Dr. Madhan, before anybody could ask, probably I would like to ask some questions to keep the session alive. I think Mr. Prasanna. Yes, sir, can you please unmute yourself and ask?
No, it is actually not a question to Dr. Madhan. It's only an observation. I think from dealing with dead collagen in making leather, Dr. Madhan has elevated himself to dealing with live collagen. and it's an excellent work. I don't know, in the days to come, it may become Central Collagen Research Institute, then Collagen Central Leather Research Institute. This is one observation which I wanted to make. But the question I have is very fundamental and rudimentary and basic. You had mentioned about triple LX, fibril, fiber, all our tanning agents, at what stage they react? Whether it is chrome or it is vegetable tannin, at what stage? Do they, I mean, my understanding was, do they go deep into the fibril at all?
Yes, sir.
Did you get my question, Mr. Madhan? Am I audible?
Yeah. I got your question, sir. I got your question. So if I can respond to it, or if you want to.
Please.
Okay, with reference to different tanning agent, depending on its particle molecular size, it's going to have different levels of interactions. For example, if I have to talk about chrome tanning, so chrome tanning also just not one species. It has about 13 different species, and one of the unique things about chrome tanning is the dimer species. If you see the dimer, which has about overall molecular size of about 11 to 12 Armstrong. If you look at the pentafibrillar level, so where 5 molecules of collagen assembled, if you look at the diameter of the pentafibrillar level, would be ideally in the order of about 12 to 15 Armstrong. And this dimer is hypothesized to fit in that ordering levels. So therefore, it can penetrate to that extent at a pentafibrillar level. Whereas if you talk about higher oligomeric species, they may not have access to that level. So now we are talking about porosity. When we start from the collagen triple helix to the macroscopic dimension of a skin. So we are talking about a pore dimension that is present within the triple helix in the order of 1 Armstrong. When it comes to the pentafibrillar arrangement, the porosity will be in the order of 10 to 12 Armstrong. And then when we come, as we keep moving, when we come to the macroscopic level as the skin, it will be in the order of about 100 microns on the highest side. So it is the restriction of these pores would influence at what level that they can diffuse, and therefore that they can interact at those levels. Since chrome can access to at a molecular level, and not only the dimer, and also the other oligomeric species will be in a position to bring about certain long-range interactions. How, like, when the collagen molecules, when they assemble into fibril, it is such interactions which assembles them into form fibril in first place. Like, here we are talking about the dimensions in the order of anywhere between 2 Armstrong to about 20 Armstrong. Like when we say about 2 Armstrong, it is the hydrogen bonded interaction and covalent interaction processes. When we talk about 20 Armstrong, we are talking about the ionic interactions. Like the ionic interaction that exists between the fibrils is actually initially driving. So such kind of long range interaction processes are one of the major factors that are associated with the stabilization in the process of tanning. So therefore, what is limiting is the diffusion and access to the site. In the case of vegetable tannins, particularly when we use the acid extracts, so that the tannins also has a tendency to aggregate with each other. So therefore, tannins typically would form a micelles kind of formation, which will be in the size of about 1 to 2 microns. And then, so first it has to diffuse into the skin matrix, and then once it goes at the fiber level, predominantly it gets coated at the fiber level in the case of vegetable tannins. And out of them, so some of them will still diffuse, and that depends on the molecular size and weight and the number of multiple chain interaction that it can create. So these are the factors which will influence the let it be a shrinkage temperature or let it be other dimensional stability when it comes to different tanning process with different tanning agents. So if I had answered your question, sir.
Yeah, thank you. It's a very, very, very interesting and very deep field. And I think a matter of half an hour or 40 minutes of presentations are not enough. I think with all your 18, 19 years of dealing with collagen, probably you would have touched only 1/10 or 1/25 of the entire subject. I think it's a very vast subject, very interesting. It's an esoteric field.
Yes.
Yeah, Mr. Omkarnath, can you unmute yourself, please? Yeah, Mr. Omkarnath, I think you have unmuted yourself, but we are unable to hear you. Okay, probably you can log out and log in. Till then, we will take a couple of questions, sir. So we have Mr. Ashok Kumar. Ashok Kumar, can you unmute yourself?
Yeah, thanks, ma'am. Good evening, sir. It's been a very long time that I am hearing from you. It was a wonderful presentation. The question which I am having is whether we could, what are the possibilities that we could use the used leather products for the biomedical application? Whether is it possible, because now global leather industry talking about producing the biodegradable leathers, whether we could, instead of if we couldn't find the way we could produce, whether we could manufacture biodegradable leather products, whether we could utilize those used leather products into different form. For example, as you presented today, whether we could use used leather products into the application. Is there any possibilities? Yeah, that's my question. Yeah.
So before I would straight away get into your question. So biodegradability, you were referring. So actually, both are contradicting. So we say, when we talk about tanning, we talk about converting a biodegradable material to a non-biodegradable. So of course, now the concepts of so-called biodegradable leather, it comes at what context? So now there are some tanning systems. Like there is one system that has been developed in the lab. From baggage, we try to you do a pyridide oxidation and then convert into dialdehyde groups functionalities, thereby bringing it into action, and therefore those leathers can it be degradable at certain environmental conditions, like after its end of life of its intended use, can it be assimilated by the environment. So that concepts are coming in, but we are yet to have any products that are commercially viable as far as the biodegradable leathers are concerned. So with reference to the existing tannery solid waste, like if you take rod trimmings, if you take fleshings, if you take chrome shavings, chrome splits. Okay. In the case of rod trimmings or fleshings, we can resort to recovering collagen to a significant extent because there is no chemical treatment to it.
Yep.
Comes to the chrome shavings. So chrome shavings, again, so there is a possibility that we can recover collagen, but not in native form, but we can recover collagen in the form of smaller fragments of collagen, like collagen peptide. It's a hydrolyzate of collagen. But but still, the challenges that it would present is, can you make such a product nil of chromium? Of course, today in our lab we are able to achieve somewhere about 50 ppm, 50 milligram per kilogram of collagen peptide. Of course, which is acceptable when it is being used as an organic fertilizer. But whether this may be used acceptable for biomedical application is another question. So still we don't. We
because
are not
of the
presence of chromium. So,
yeah, thank you, sir. Yeah.
Yeah. Next on line is Mr. Saravanan S. Can you unmute yourself and ask the
Yes,
question?
ma'am. Yes, ma'am. Thank you so much, ma'am. Thank you, sir. It was really a great evening session. I have two doubts, sir. The first one is in the very last slide, you are explaining that the extraction of collagen from the leather making wastes. Is this the only way, or we can utilize the collagen extract from the raw material itself, sir? When it has a economical value and other things, why not we can try in those aspects?
Absolutely. So those are some of the research thing, that we are getting into today. Of course, it is much more economically viable if you think of raw material which are of very low selections. Okay, so now today the buffalo hides, particularly during even prior to the COVID lockdown. So I was told per kilogram of buff hide are being available at around 10 to 15 rupees. If that is the case, yes, it is viable to recover collagen and make products out of it. But if it goes beyond 15 rupees, again you need to pitch it on high value, some slightly very high value. But again, demand, for such biomedical application is very, very minuscule. Okay, right? So from one buffalo hide, you can make collagen materials for thousands of patients. I mean, thousands of collagen materials, because like each collagen scaffold, it requires only about 100 milligrams being present part of it. So therefore, it again depends on the viability of the business to look at can I build and create a huge investment and recover collagen or its products to be used into a biomedical product where the volume is very limited. The absorption volume is limited. Of course, there are also options to take such collagen into FMCG. So once you pitch it into FMCG, then the market volume absorption is wide open. And similarly, if you can pitch it into a fertilizer application, again the volume is huge. Again, the value in such high volume applications is lesser. And now the question is, a good raw material, good quality raw material. In my opinion, it may not be at the moment, it may not be viable to convert high selection raw material absorbing into such kind of alternative application. And certainly, yes, a low grade raw material today, it is highly viable to pitch in for such alternative applications of collagen, including extracting collagen and using those collagen. Of course, collagen is picking up in a big way. So the market of collagen is also growing significantly, but then it is nowhere near the market of leather and leather products industry. Leather and leather products industry is about $150 billion, whereas collagen market is currently about around $5 billion. So it's nowhere near.
Okay, sir. Okay, sir. Thank you so much, sir.
Yeah, Mr. Omkar Nath. Probably you can unmute yourself and ask.
Yeah, I have unmuted. Can you hear me?
Yes,
Yes.
sir.
Now you can hear me.
Yes. Sir.
Okay. Actually, we in Flamingo, we are now we have the rejections in the raw level. Actually, we do the selections of the material at the lime stage after the fleshing. Okay, and then we reject certain material, and we are right now converting that into the CP, that is collagen peptide hydrolysate right now. And then we are converting into the chicken feed now, actually. That is what we are doing it. And we are experimenting it to the, with our own kind of chicken farms, actually. Okay. In that particular thing, I just want to, I just shared in a crude way, we are doing it. And this is a sort of, this is what Dr. Madhan speaks is a very a sub product which is much higher in terms of utility and in terms of value, etc. And is there any other way of converting this? hydrogen, CP hydrolysates. This is what my question is actually.
Okay. Yes, sir. So certainly, you can pitch it for higher value application, but investment requirement will be very high. So, you go through a series of, purification, filtration, purification, and sterilization and spreading process, where the investment scale requirement is very high order.
Oh, I see. Because right now we have about 5% of the total purchases. We are making this rejection is taking place actually, which we are converting right now as a chicken feed only.
When we talk about chicken feed, the market, per kilogram of the
No, we are not making it for the market. It is for our own. Our company boss has got another farm, a chicken poultry farm actually, where he is trying to use it actually.
And just to share
so right now, what we are thinking is
just to share some interesting, work that we did with CFTRI, Central Food Technology Research Institute. So we tried some of these collagen peptides, and then particularly for, I think, poultry, we use it for mice, rats. So what we found, so usually, when we use protein, the bulk of the mice will grow faster, being a protein. But in this case, it did not build weight, but at the same time, it was very active. So we were wildly thinking, maybe the assimilation ability of such peptides is quite high. So probably this can be targeted as a concept associated with, say, weight reduction foods, things like that. It's just
okay, good. Okay.
Now, just to add, collagen peptide, like there is a Nita gelatin, they are making a collagen peptide from bone.
Okay.
So they take it through a process of extracting gelatin and then subjecting them to enzymatic hydrolysis to form these collagen peptides. And these collagen peptides are now used for arthritic applications, anti-arthritis application. Now they sell them in the form of sachet, formulated sachets, which is available at around 20 rupees. But then if you see, the effective volume that is part of sachet is not more than, effective weight is about 0.5 to 1 gram. 1 gram is about 16 rupees. But then the collagen peptide within that 1 gram is not more than 100 milligram. So the active ingredient is just 100 milligram. But what is being sold in market is somewhere about 20 rupees. So now you can imagine, now that's a very big market, particularly for arthritis, anti-arthritis application. There are a lot of people are coming into big way. So there are many pharmaceutical manufacturing companies who are using such collagen peptides, formulating products for orthopedic applications. So those are the areas where the value proposition can be very high. So therefore, yes, it depends on.
Thank you very much, sir.
You can, again, depends on the investment scale, depends on the process. You can pitch it in different value scales. As I was mentioning before, the volumes are different.
Okay. It's very nice, interesting, Dr. Madhan. And I think I would also like to consult with you from some time
Pleasure to
in this regard, actually.
Yes, sir.
Okay.
It's 6 o'clock.
Thank you.
Any more questions, please? I think there are no questions further, looks like. So I would like to thank Dr. Madhan for his enlightening lecture. And now may I request Mr. Nachiappan to kindly propose the word of thanks. Mr. Nachiappan.
Yeah, Dr. Sarna, thank you, Dr. Madhan. It was a wonderful session. The calm and composed way you were teaching, it was very good. Thank you very much, and I thank all the participants. there are around more than 60 registrations. When we started, I was telling Dr. Madhan it was 43. Then it shoot up around 60, 65 people are registered. And now around 35 to 40 people were able to attend, with some people having some difficulty in attending, probably of internet. Can I call upon Mr. Mishra to summarize the speech? Mr. Raji?
Yeah, thank you very much, Mr. Nachiappan.
Yeah.
This has been a beautiful presentation by Dr. Madhan. And while trying to summarize the presentation, I must quote Tori Amos, who says, healing takes courage, and we all have courage, even if we have to dig a little to find it. We are fortunate to have Dr. B. Madhan, a soft-spoken person with visible ability to transmit his concepts in simple ways to comprehend. Dr. B. Madhan started his presentation by explaining type 1 and type 2 collagen, their triple helical structures. He also explained the supramolecular assembly of type 1 collagen and the glycine XY repeat structure, hierarchy ordering of collagen chain, chain to molecule, molecule to fibril, fibril to fiber, and fiber to tissue. He very much explained the differences between cornea and skin that has given the background for the whole presentation. And then the glycine mutation to other amino acids, which has been leading to osteogenesis imperfecta. Stability of triple helix when glycine is replaced by other residues. He has also unraveled the mystery of osteogenesis imperfecta, where larger residues are harder to be incorporated for glycine. Then he has covered the subject of collagen stabilization in length, hydrothermal stability of collagen fibers, treatment by condensed tannin polyphenols, conformation of collagenase on treatment with condensed tannin polyphenols, collagenase hydrolysis of native and RTT treated with various tannin precursors exhibiting higher thermal stability. Then he touched upon the lessons from vegetable tanning to managing arthritis, autoimmune disorders, rheumatoid arthritis and its articular cartilage composition. And the topic of vegetable tanning of cartilage was explained in great length. He also took the examples of stabilizing bovine articular cartilage against collagenase. Also, he has shown the pics regarding the H&E stained sections of rat joints therapeutically treated with polyphenols. Intra-articular administration loading polyphenols. And then he has covered the section of chronic wounds, the biochemical challenges that are posed by the chronic wounds, degradation and regeneration of normal tissues, collagen sponges suitable for chronic wound application, how effective and how affordable they are. Then he has explained about the various scaffolds. Wound healing, he has explained, and we have seen how the good healing has occurred in day 15. Also, he touched the topic of healing chronic wounds of leprosy cured but deformed personnels. And then he touched a very important topic of diabetic ulcer and the three factors associated with the healing of diabetic ulcer, which is low cost, lesser dressing requirements, and faster healing. He has given a very beautiful thought to tap the potential of collagen, as at the moment we are tapping out of 300 just 140 for leather. Collagen is so precious, as we have seen, that no one would dare to waste it. He has beautifully answered the queries posted by Mr. Prasanna, Mr. Ashok, Mr. Sarvanan, Mr. Omkarnath, and others. Lastly, I must say, it's often said that rain helps us appreciate the rainbow. That's true for any of life's challenges. Facing problems and struggling every now and then are simply inevitable. But God has given us people like Dr. B. Madhan, who are struggling hard to make our journey more comfortable and pleasant. Thank you very much.
Thank you, sir.